Hello, hello, hello. Hopefully you can all see me and hear me. Please feel free to say hello. Welcome to our A-level class. Apologies for that. We have been having a couple of technical difficulties this end, so hopefully we're all sorted and it's all good. Please let me know if you can hear me and see me, etc. And I'll just get my screen sorted. Oh, I'm going to drop everything again. No. Oh, there we go. Right, let's get that screen sorted so that I can see what you're saying. Hello, welcome. Hello to those of you who were in our GCSE class, and welcome to those of you who've just come for A-level. It looks like we've got lots of people here, which is amazing. So welcome to everybody. Those of you who are in year 12, of course, you're welcome to be here. Please feel free to ask as many questions as you can, because hopefully we've got some very knowledgeable students in our chat who can help you. And if you aren't confident with answering questions with asking questions and just want to sit and absorb, that's also absolutely fine. So really nice to have you guys here. Welcome to those of you for whom this is your first YouTube class, welcome. And to those of you who have been to many of ours before, then welcome back. It's nice to have you guys here. Yes, this is we're just going to be looking at aldehydes and ketones in this session. So only those two carbonyl compounds. Because there does seem to be a lot more of you, please feel free to send your question more than once if I don't respond to it in a timely manner. It might be that I've missed it and it's disappeared off my screen. So please, let me know if I don't see your question. Can you all see my PowerPoint? I've seen that one person said they can, one person said they can't. I should be sharing it, so you should be able to see my PowerPoint screen. So please let me know if you can't see it. If everyone, okay, it looks like people can see it. So if you can't, it might be your screen. You might want to have to refresh or something. Thank you guys, you're brilliant. Thank you so much. Perfect, lovely, good. That sounds fantastic. Awesome. Okay, well, I'm excited to get started. So let's have a look at what we're doing today. So for those of you, I've seen there are obviously some names that I recognize and some people have said they've been here before, but if you don't know me, I'm Alyssa. I am the lead GCSE chemistry teacher and A-level teacher at Snaprovise. I've got a PGCE in chemistry education from Oxford University. That was quite a while ago now, and I've been teaching A-level chemistry for over 6 years. A-level chemistry is my favourite, but I also teach all the other sciences up to GCSE as well. So chemistry is my fave. Thank you very much. That's very kind of you. Okay, so just so that you guys are aware, right now we're doing our back to school offer, which means that you can get 25% off courses, which is off your first month's subscription, which basically means you get a week for free, which is pretty good. So back to school 21 is the code. If you want to use it, please do. You can copy and paste it, or I will be showing it again at the end of class. So if you're interested in getting involved in our courses, then feel free to make the most of this offer, which is a fabulous offer. So back to school 21 is the code. It gives you 25% off your first month on our courses. Like I say, I will show you round that at the end of our class. So, and I'll pop this back up so that you've got a chance to have a look at it again. But we will get on with our lesson first. I'm going to try and push through and make sure see if we can make up for the lost time. So apologies for that. Is there any good scope of studying medicine in the UK? Do you mean, is medicine a good place? Is the UK a good place to study medicine? In which case, yes, definitely. I've heard lots of people have an amazing time studying medicine here. Right. So what we're going to do this lesson, or this is going to be just less than an hour because we're a little bit behind at the moment, but we're hopefully going to recall our nomenclature, how we name our carbonyls and some of their properties. We're going to specifically look at aldehydes and ketones. Then we're going to understand how oxidation of carbonyls can be used to identify them, so identifying tests. And then we're going to understand and draw the reaction mechanism of nucleophilic addition reactions. We're not going to look at hazards of KCM, which is something you do need to be aware of. We're not going to look at the dinitrophenylhydrazine test because I think that only comes up in one of the specifications. And we're not going to look at the optical activity of carbonyls because that's quite a big content, quite a big chunk of carbonyl chemistry. So you're going to need to look at that yourself. / we do cover it in some of our other classes. So if you wanted to come along and join our classes, we will cover some of this stuff in those classes. Okay, so no worries, let's go. So one of the most underused but most useful resources for A-level students, I think, is your specification. It is literally a checklist of everything you need to know. So we've included it at the beginning of our PowerPoints so that you can use this to check what it is that your exam board wants from you. So this is the checklist for AQA. So this is what we're going to be covering from AQA. Bear in mind though, as I've just said, we're not going to look at those 2 points there. So you will need to cover that yourself because that's specific to AQA. This is the OCR specification. So again, if you are an OCR person, this is what OCR is expecting from you, what you'll need to know or be able to do in order to do your exam. And again, we're not going to be covering 2,4-dinitrophenylhydrazine because that's just OCR. And Edexcel, we haven't forgotten about you as well, Edexcel students. This is what Edexcel expects of you. You'll notice they're very different, the specifications. So get yourself acquainted with your specification because they are so useful. But here again, we're not going to be looking at dinitrophenylhydrazine and we're not going to be looking at the optical activity either. Okay, sorry guys. For AQA, yeah, it's KCN toxicity. Yeah, exactly. And 2,4-dinitrophenol is in AS levels. Would you cover it? I'm not sure you would cover it in AS levels, actually. I think it probably would only come in the A2 content, the year 13 A2 content. Especially if you look at whereabouts it is in the specifications. That's quite far on in the specifications, so I think it does come in A2. Cool, lovely, fantastic. Okay, so what do we already know? This is stuff that hopefully we already know. What's a primary alcohol? What's a secondary alcohol? And how do we differentiate between them? And then what do we need to add to our primary alcohol or our secondary alcohol to what reagent or conditions do we need to get an aldehyde or a ketone? Anybody know? When do we do AS content? So we do some AS content, usually a little bit later on in the year, but we do try and flip between the two. So we do some AS and some A2. And if you wanted to join, if you want to look back through our web classes, you'll see that there is some AS content in there. And also if you want to join our courses, we do AS content every week. We do at least 1 hour, if not 2 hours of AS teaching every week as well. Okay, so just checking I haven't missed anything. Lovely, thank you, Lucy. Brilliant. A primary alcohol is when the carbon of the OH is attached to one other carbon. Primary for one, singular. So fantastic. So our carbon, actually I'm going to go to blue, not red. So the carbon of our alcohol, our alcoholic carbon, as it were, is only attached to one other carbon, which I'm going to represent as an R group. Otherwise, it's attached to hydrogen. So it's only attached to one other carbon, that makes it primary. And therefore secondary is when it is attached to 2 other carbons. And then obviously the leftover must be a hydrogen. Brilliant. Well done, Eleanor, as well. Fantastic. I'm going to, apologies if I pronounce your name wrong. Mushafi, well done as well. That is brilliant. Good. No, we're not talking double bond. I don't know what I'm not 100% sure what functional group we would call that, but that would change the functional group. I don't know that you would necessarily call that an alcohol if the carbon was doubly bonded to another carbon, because it'd be a double bond, so an alkene group directly bonded to an alcohol. So you're unlikely to find that, especially at A level anyway. Good questions. Fantastic. Okay, so I have seen it, and well done, Chem Medic, as well. What is it that we need to turn these things from alcohols into either an aldehyde or a ketone, and it is acidified potassium dichromate. Now, you need to read the question carefully, but often you can either write acidified potassium dichromate, as in words, or you can write out the formulas. So K2Cr2O7, and it's acidified, so you must include the acid H2SO4 in order for it to be acidified. Really good. Well done, those of you that put that in. That's fantastic. Awesome. Okay, so then aldehydes and ketones. Hopefully we know the difference already. An aldehyde, what is the difference? I think I've seen somebody put it already. Oh, fantastic. Ken Medic for putting the change in color. That's awesome. So good question. Could we not just do K2Cr2O7 with H+? They sometimes will accept that. If it's asked you to name the reagents, I don't think they would allow it, because you're not naming a reagent, you're kind of giving a condition. But if they just ask for the reagents and conditions, I think you probably could say /H+, because you're implying that it's acidified. So you just need to check exactly how the question is worded, and they can be really mean sometimes. And if you're not sure, then you could put both. You could say /H+, e.g. H2SO4, then you know you've covered all bases. Awesome. Fantastic. It looks like a couple of you have got this already. So ketone, I always remember it, ketone is a smaller word, and therefore the functional group is smaller. So ketone is the C double bond O. The aldehyde, the longer word, has a longer or larger functional group. So it's the C double bond O with a H attached to it. And then we have got our R groups of some kind. So our carbon chains of whatever kind there. So that makes our aldehyde and our ketone. Awesome. Yes, so somebody has mentioned it. How do we get our aldehyde versus our ketone? What do we need to do in order to stop our aldehyde from continuing the oxidation onto something else? I think somebody's already mentioned it. What do we need to do? Yeah, good, well done. We need to distill. We need to distill, so we need to separate off the aldehyde once it's been made. Otherwise, it will keep going to become a carboxylic acid, which we're not necessarily going to look at in much more detail. We'll see. So that's some good information there. Raj, so I can't read, my screen's a bit funny. Rajdeep, however, you're going back the other way. I think you're trying to reduce it rather than oxidize. So just be careful that we're going the right way. And yeah, lovely. So we can reflux off, we can distill off the aldehyde to make sure that we get our carboxylic acid. But if we are doing our secondary alcohol, we can just reflux it, because it's very unlikely that we're going to get any carboxylic acid coming off a ketone, because you can't oxidize a ketone to a carboxylic acid. You can't stick an OH where there is an R group. It's just not going to work. So we can't oxidize a ketone. So we can just whack it under reflux. Okay, cool, lovely, well done. We're not going to look at the mechanism yet. We will look at a mechanism later on. Hopefully we'll get to it. So super quick then. 1 carbon, 2 carbon, 3 carbons, 4 carbons, 5 carbons, 6 carbons. What is the nomenclature? What are the prefixes that we need to use to talk about something with 1 carbon, 2, 3, 4, 5, or 6? Get typing, get them out. What are the prefixes if we're talking about an aldehyde or a ketone, for example, with 1, 2, 3, 4, 5, or 6 carbons? It's not due to the inductive effect, it's due to the fact that our ketones, good question though, our ketones have got an R group already. If you look at a carboxylic acid, it's not got an R group on it, it's got an OH. Now, our aldehyde can be oxidized the hydrogen on the aldehyde can be oxidized to an OH, but if we were to oxidize the R group on a ketone to an OH, we'd have to break a carbon-carbon bond, and that is you're going to need a lot of energy. You're also going to kind of break up the structure, and that's very unlikely to happen in a reaction. So we can't oxidize a ketone to a carboxylic acid. Good question though. Lovely. Looks like loads of you have absolutely smashed this. So we've got meth, eth, prop, bute, and hopefully we know all of these from GCSE. And then we go on to say pent and hex, and then we can go on even further if you want, but we're not going to do that right now. So what's the oxidizing agent for secondary alcohols? The same thing. I've just written it out as in the chemical form rather than the word form. So it's acidified potassium dichromate reflux. Great answer there, Lucy. Thank you very much for answering that. That's awesome. Well done. Really nice answer. Awesome. Okay, so speeding on then, let's have a look at our basics of aldehydes and ketones, which looks like we already know quite a lot about, but we'll just double check. Oh, good luck, good luck. I'm sure you'll be amazing. So our suffix for aldehydes is what, and our suffix for ketones is what. What do we use? What's the suffix? What's the ending of the words that we use for ketones and aldehydes? Can a secondary alcohol be oxidized using reflux or distillation? I don't think you would be able to do it with distillation because I don't think you get it hot enough. So I think you need to use reflux because you need to get it hot enough in order that it will oxidize. So good question, but I think, yeah, you would need to use reflux. You'd need to get it hot. And we don't need to use distillation because distillation is removing the product. And we don't need to. We might as well just leave it and let it reflux until it finishes, till it completes. Fantastic. Looks like everyone's nailed that. So our suffix for aldehydes is al, something al, e.g. propanal. So propan, meth, eth, prop, 3 carbons with an aldehyde on the end, propan, al. And then our ketone, our suffix is -one. For example, butan. Oh no, I shall go for propan again, so I'm not confusing things. Propanone, so 3 carbons with an -one, with the ketone in there as well. And numbering, exceptions for aldehydes even. Let's do that first. Our aldehyde exceptions, we call nearly all of them aldehyde, apart from when you've got benzene, which we sometimes call benzaldehyde or benzene aldehyde. Benzene is a bit weird, especially naming with benzene. So I often say don't worry too much about it because they're usually quite lenient with their names for benzene. So we call it benzene aldehyde or sometimes benzaldehyde, so it's a bit odd. And numbering with our ketones, when we're numbering with our ketones, which end do we start numbering from when we number ketones? No, usually when we say reagents are cold, we mean room temperature. I don't think you'd ever name something, you'd ever state anything's cold, apart from maybe water. But even then, I think you'd probably state room temperature rather than, it's usually a comparison between room temperature and hot generally. So that's a good question. Okay, so Kurt, if that is in answer to me, my question about numbering, it does matter. It does matter. So if we've got 1, 2, 3, 4, 5. So I've got 5 carbons. The end of each line or the join of each line is a carbon. If you've not met skeletal structures before, I've made a mess of that. Let's do that again. So I've got 1, 2, 3, 4, 5 carbons. So how do I name or how do I number this ketone? Yes, good. Well done, Chem Medic. It's always the smallest number. So we don't go 1, 2, 3, 4. We don't say that the ketone's on carbon 4 when we could number from the other end and make it carbon number 2. That makes much more sense to number, and we always number the lowest number possible when naming our priority functional group. So we start with the lowest carbon number possible. Oops, can't spell. E.g., this one is 1, 2, 3, 4, 5 pentan 2 ohm. Yes, exactly right. Well done. So we start at the priority, which is they start at the end, which is closest to our priority functional group. Good. And so what we always do, so you always know that your priority functional group, the one that is named at the end of your name, that's your priority functional group. We always know that that is at the carbon with the lowest number, or it's at the shortest end of the chain. Good, fantastic. I'm glad you think that. That's why we do it, because that's what we're trying. That's what we're trying to help. This is what all our classes are like as well. So if you fancy joining us on our web classes, then this is a good example of what our web classes are like. Okay, so let's have a quick look at our properties. Cold. I'm not 100% sure what you're referring to there, Rajdeep. Sorry, I can't be very useful to that. Apologies. Let's just look at our properties of aldehydes and ketones. So the permanent dipole of a carbon-oxygen double bond, I pressed a button, go back, determines much of the properties of aldehydes and ketones. What we can see here is our our alcohol boiling point increasing gradually, our ketone boiling point increasing gradually, our aldehyde boiling point increasing gradually, and our alkane boiling point increasing gradually. You'll notice though, our ketones and our aldehydes have a higher temperature boiling point, naturally have a higher temperature boiling point than our alkanes, despite the fact that there are the same number of carbons. That is because of this CO double bond, because we've got an electronegative oxygen attracting the electrons in the double bond, and therefore an electropositive carbon, a delta positive carbon, means you've got a permanent dipole, and therefore there is permanent dipole forces between molecules, therefore, and they're stronger than just our normal London intermolecular forces that you get in alkanes, hence it's higher. And I won't mention alcohols. Oh, why not? Why are our alcohols even higher? What do alcohols have that ketones and aldehydes and alkanes don't have? What's present between molecules of alcohol that means they, oh yeah, it looks like someone's already said it as well. Hydrogen bonds. So there's H bonding in alcohols, meaning they've got an even higher boiling point. Ketones and aldehydes have permanent dipoles. What is a dipole? That's a really good question. A dipole, di being two, pole being poles of a magnet, poles north and south pole. It's opposites, polars, poles. So a dipole, two poles, a positive and a negative end, basically. So a dipole in a bond is when you've got a negative end, a partially negative end, and a partially positive end. That's a dipole, a split charge, basically. That's a good question. Yes, lovely, well done, everybody who said that. And then our alkanes only have London forces. That's the kind of strongest intermolecular force between our alkane molecules. It's just London forces. Hence, they have the lowest boiling points. So ketones and aldehydes have London forces and permanent dipole-dipole interactions, and then alcohols have all of those and hydrogen bonding. Cold. I don't think I've ever seen, especially not A level, I don't think I've seen the term cold used, Rajdeep. So I would not worry about it too much. Yeah, I don't, and whenever I've used potassium permanganate, I've only ever used it at room temperature. So sorry, I don't think I can be more useful to you there. Lovely, well done. Okay, so solubility in water then. Do we think aldehydes and ketones are soluble? How soluble are they? What do we reckon? Think about what's necessary for something to be soluble in water and what we have present in aldehydes and ketones. So what do we need in order for, so water is a polar solvent. So in order for things to dissolve in water, to be soluble in water, they also need to be polar. Good, we need to have polar groups. And we have a permanent dipole. We have a polar bond, our C double bond O, in both aldehydes and ketones. So we do have polar groups. What happens though when we get our really long chain aldehydes and ketones? What do we think? So our short chain aldehydes and ketones are partially soluble. They can dissolve. I'll just say are soluble in water because they have got this polar C double bond O bond. Yes, well done. Good, fantastic. Looks like lots of you have said longer chains are less soluble. Longer chain molecules. Why? Why are our longer chain molecules less soluble? Why are they going to be less soluble? If I've got a lovely long chain aldehyde, why are they going to be less? Yeah, good. We've got more van der Waals forces, or more of the chain is not polar. A large proportion of the molecule is not polar. So the big bit of the, this big chunk here is not polar. So it can be very difficult, or you're going to get a lot less being able to be dissolved in water because this chunk is not polar, it's non-polar, so is more likely to be, why is the word eluding me? Where it's insoluble, the opposite of soluble, not insoluble, but the other one. Brain. Hydrophobic, that's the word I was looking for. Is that applicable to all soluble molecules? I think it does depend on why it is soluble. So if it's soluble because it has got a complete charge, I don't think the effect matters so much. However, because you can get fats, really long chain fats that are soluble, but I do think it depends on kind of where the polar group is in terms of and how many polar groups you've got as well. So you could have a ridiculously long molecule that's got lots of polar groups on it. So in which case that would be soluble because it's got lots of polar groups on it. So, actually we don't tend to talk about this a huge amount anyway, but it is just something we need to be aware of. So this bit does our London forces and therefore is not going to be as soluble. Polar end. Amphipathic, that's a great word. I'm not sure I know what that word is. So I think I've missed a couple of questions. Let me just double check. The delta positive side is more positive. Yes, it's Yeah. Because, yes, because carbon has got protons in the center of it, in its nucleus, the protons are positive and the electrons around the outside of the carbon atom are negative, which is why all atoms, if we're talking about an atom, a single atom, all atoms are neutrally charged because they've got equal numbers of protons and electrons. So if you start removing some of the electrons from around an atom, it becomes ever so slightly positive. So London forces and van der Waals are basically the same thing. Depends on your official definition. Some people like to argue that they are different. At A level, I believe in all exam boards, we don't need to say van der Waals anymore. We can just talk about London forces, which just talks about instantaneous induced dipoles that occur. And it's kind of like an umbrella term for all of the weaker intermolecular forces, which we at A level only consider to be instantaneous induced dipoles. I hope that answers your question. Yes, so as far as A levels are concerned, London and van der Waals are the same, and just stop saying van der Waals, stick with London. So aldehydes and ketones are soluble because they're polar, yes, good, but the longer chains we get, the less soluble they get. Lovely. Weakest at A level, weakest intermolecular force that we come across. I can't think of anything that we would say is weaker, but we'll say weakest. Right, quite a lot of theory we've just gone through very quickly there, so just let me know how you're feeling about that. Give me a 1 if that was fantastic. I'm super happy with that. That was really easy. Give me the next one. Give me a 2 if it was okay. I'm gonna think about it a little bit. I can probably keep on top of it, it'll be fine. Or 3, oh my gosh, no, that was horrible, hated it, never going near it again. Okie dokie, cool. So we've got a mixture, which is absolutely fine. That's what we expect. So let's have a go then at this exam question. So 2 organic compounds, X and Y, both with the molecular formula C4H8O, contain a carbonyl group. Give the structural formulae of the 2 possible isomers of Y, which are aldehydes. So just have a think. I'll just give you a second to have a think. We're giving the structural formula of the 2 possible isomers of Y, which are aldehydes. We can ignore X for now. So it's an isomer of C4H8O, which are aldehydes. So just have a think. ChemMedic's given an answer. Have a look at what they've given. Decide if you agree or disagree, if you want to make a change or if you want to say something different. We want 2 structural formulas of 2 isomers. Good question. Let's have a look. So I'm going to have a go at drawing out what ChemMedic has put. So they said, oops, I don't know why I'm writing over there. It's right over here. CH3, CH2, CH2, just checking the number of carbons, looks good. CHO, which should look, if I draw it out as a full displayed formula, CH2, CH2, COH. So it's an aldehyde. Good, that's what we wanted. If our functional groups go on opposite ends, all we'd be doing there would be kind of flipping the molecule around or looking at it from behind. So we can't just move the functional group. It's an aldehyde, so it has to be, yeah, good. They would be the same. They would, it's an aldehyde, so we have to stick the functional group on the end. There's a really nice little flag to have in your brain when you think about carboxylic acids and aldehydes, is they're always at the end of chains. That can often be really useful when you're trying to think about isomers, when you're trying to think about mechanisms, etc. So carboxylic acids and aldehydes are usually at the end of chains. So there's only 2 places in which you can put them ever. So good, not, yep, good. Yes, lovely. So if we had 2 aldehydes as well, we'd need 2 oxygens, exactly. Good questions. Can somebody answer that question? What's the difference between a structural and a displayed formula? What is the difference? And I'm just going to write out, I've seen some really nice examples of some other structural formulas for our second isomer. So I'm just going to draw that out. So we have CH3, 2CH. Yep, CHO. So I was just double checking how many hydrogens we have there. So that would be something like that. So we've got 2 CH3 groups attached, and then we've got our aldehyde group. So that's lovely. So structural and displayed, yeah, lovely. So most of us, it seems, are quite happy with the fact that displayed formula shows all bonds, including OH bonds. You need to make sure you show all bonds if you're asked for a displayed formula. Structural formula shows the 3D, so it shows the order of atoms in a structure, and they should be able to be read by anybody and drawn out by anybody. What it doesn't show is relative 3D space that we would need to be shown with our E, Z, or cis trans isomer nomenclature, but you should be able to draw a full displayed formula from a structural formula. So what we do is we read from left to right, and you can see what's bonded to what, basically. Okie dokie, that looks good. So they are partially soluble, Eleanor, but they get less soluble as they get longer. I'm not sure what the cutoff is. I'm sure there would be a cutoff where we would say they're insoluble, but most things are partially soluble, as in like tiny amount soluble in water, even if it's only a tiny amount. Most things will dissolve a little bit in water. So we just have a cutoff where we say, nah, that counts as insoluble now. So there will be a point at which they become insoluble, but we don't have to know when that is, and I don't know when that is. I'd need to look it up. Good. Okay, so that's our formula there. Oh, we're so running out of time. We might not have time to do exam questions. Sorry, guys. Or maybe we'll do the exam questions instead because it covers the same content. We'll see. Right, reactions of carbonyls. How would we name a compound with two aldehyde groups, one at each end of the molecule? I'd call it a dial, probably. Just the same as you'd call it a diol or a dione or dicarboxylic acid or dioic acid. I'd call it a dial, because you know that it has to have two. Oh, thank you very much. You know that the aldehyde groups have to go on the end of the chain, so we don't need to like give a number to say where the groups are. It would just have to sit either end. So I just call it a dial. If you had, this is getting super complicated now, but if you had an aldehyde on like the main chain and then you had a little branch with an aldehyde on it, you would name the branch as an aldehyde group, and then you would name the full chain, the longest chain, as the main carbon chain, as it were. So then it wouldn't be a dial, it'd be an aldehyde or something al, and then your group, one of your substituents, would also be an al group. But that's getting super complicated, and we wouldn't be asked to do that at A level, so that's all right. Right, reactions for carbonyls. Let's see how far through this we can get, because otherwise I'm going to run over. So, oxidation. As ketones are in the middle of a carbon chain, as we've already spoken about, they are not readily oxidized. So we've already shown that we can oxidize a primary alcohol to a ketone, but we can't then take a ketone any further, because we've already got, our carbon is already bonded to as many carbons as it can. The only way we would be able to oxidize it further would be to either break a carbon-oxygen bond, which makes no sense because we're trying to oxidize it, we're trying to increase the bonds to oxygen, or we'd have to break a carbon-carbon bond. And that, again, is not going to happen very easily, and it breaks up the molecule anyway, so it wouldn't be very useful. We're not going to look at the iodoform reaction. Sorry, no. Sorry if I lost you. I wouldn't worry about it. I was overcomplicating it, and we're not going to look at that at A level anyway. So I was just trying to overly answer Gia's question. So apologies. So aldehydes, however, can be oxidized to a carboxylic acid, as we've already looked at in this session. So our aldehyde we can increase the carbon-oxygen bonds by adding in an oxygen there. Good question. What are we distilling off? When we go from primary alcohol to a ketone, what are we distilling off? The aldehyde. Yeah, we're distilling off the aldehyde. We remove the oh, what have I done? I've done to a ketone there. Oops, sorry. Didn't mean to do that. Let's do it here. So when we're going from a primary alcohol to an aldehyde, can't write quickly. We distill off the aldehyde because that will have a lower boiling point than our carboxylic acid. So if we distill it off before it can react to a carboxylic acid, then we've got our aldehyde, and it doesn't go all the way to a carboxylic acid. If you left it under reflux, it would go all the way to a carboxylic acid. Nice. So what are the color changes for these reactions? This is identifying, or our tests that we can prove we have got either ketones or aldehydes. So what are the changes, and where would they change for, where would they be different? What are the color changes, and where would they be different for ketones? We need to know what the different color changes are and where they would be different for ketones. We'll start with acidified potassium dichromate. Lovely, good. It's orange to green. Let's get my colors up. Orange to green. If it oxidizes. So if oxidation occurs, it goes from orange to green. If no change happens though, then no oxidation has occurred. Therefore, if we've got a ketone and we try and oxidize it, then we will see no change because it won't oxidize. Lovely. We've got some tolerance stuff coming in, which is great. So our, can I do this in white? Oh yeah, you might not be able to read that particularly well, but Tollens, which is, looks what you guys have got. Oh, good point. I can't remember specifically for OCR. If you have get your specification up and just search for Failings or Benedicts and see if you can see it in the specification. If it's not there, then I think you're right, it's not present. So with Tollens, we go from colorless to silver mirror, which lots of you have said, which is amazing. It's a really cool experiment if you get the opportunity to do it. Silver mirror, colorless to silver mirror. And again, there is no change for ketones because oxidation won't occur. And if anyone has met Failing solution or Benedict, oh, Fatima says Brady's reagent for OCR. So it might be worth checking that as well. Thank you. So Failings, you might have met it in biology. So it goes from a deep blue to a brick red. Don't know why I did my arrow in that color. Oh well. If oxidation occurs, oh dear me, my handwriting is getting scrappy because I'm trying to write quickly. But there is no change for ketones again. Okie dokie. Yeah, Cool, that's fine. So these are all oxidizing agents, and the tests or observations that you would see when using that oxidation test. Oh, thank you. Yeah, lovely. Okay, right. Let's keep going, see how far through this we can get. So, as we're rapidly running out of time, so apologies. So, oh, I just clicked my shoulder. So, reduction, both aldehydes and ketones can be reduced to primary and secondary alcohols, respectively. So, we're going back the other way. If you can oxidize from a primary alcohol to an aldehyde, or from a secondary alcohol to a ketone, then you can go back the other way. So, and I think I've seen one of them previously, haven't we? What would we need? So let's go from, let's do our aldehyde. What do we need to add? What are our reagents and or conditions to go to oxidize back to? This is A2. This is lovely. Okay, good. So you'll notice that we've got two different chemicals. Lithal with our 4 hydrogens is one of the reagents that you can give, or you can give sodium borohydrate. But that, I believe, is AQA only. I think everyone else needs to give lithal. So just double check that you're happy with that. And how much time? We haven't really got enough time to go through the proper mechanism. We're going to speed through the mechanism. You don't actually, again, double check your specification, because you don't always need to know this mechanism for reduction. In fact, I think OCR maybe is the only one that needs to know. You don't quote me on that. I'm not 100% sure. Oh, you can use sodium borohydride and OCR as well, can you? Thank you. I've gotten written down that it's only AQA, so I may be wrong on that. That would be worth checking. And OCR do need to know the mechanism. So who is it that doesn't then? Maybe it's AQA that doesn't. Oh, I'm confused now, so ignore what I'm saying. But let's go through the mechanism before we run out of time. So we can use our, I should just put them, oh, what's happened? Okay, we can use our lone pair, or put our lone pair there. Whenever we're doing mechanisms, I'd like to talk through this a lot slower, but I've run out of time. If you're ever not sure, or you haven't got an amazing memory, don't memorize mechanisms. Work them out. Understand how these chemicals would interact with each other and work out what is going to happen. We've got a hydride. That's what these two chemicals are. They are sources of hydride, H minus. They're sources of hydride ions, H minus. So we've got a hydride, and we've got, in this case, our aldehyde. What's present on the aldehyde? What have we got? We've got 2 lone pairs on the oxygen. We know that it's electronegative, so it's got a delta minus, and we know we've got a delta positive carbon attached to it. So how is our negatively charged hydride going to interact with this? It's going to attack the positive center. I'm not 100% sure, guys, so rather than tell you wrong, if you look through your specification, it specifically always uses the word mechanism, if you have to know the mechanism for a reaction. So this is a type of nucleophilic addition, because we are adding a hydride to our to our positively charged center by the donation of a lone pair. So this is nucleophilic addition. So if you search for nucleophilic addition in your mechanism, in your specification, if it says mechanism, then you know you need to know the mechanism. Lovely, thank you very much. Lovely to have you. I will see you soon. So once that hydride has attacked that positive center, then we have got that carbon would have 5 bonds. It doesn't want 5 bonds if it can help it. And luckily, our oxygen is very electronegative, so it's already partially broken that double bond. So the oxygen can very easily accept that lone pair, that pair of electrons onto it to become a O minus ion, or a oxygen with a minus charge. And then we would need to acidify our product, our intermediate. So we would need to add H plus in order to create our alcohol. So that would almost be a second step. We would need to acidify. We'd need to add that hydrogen. Otherwise, we wouldn't have. We'd have a salt or an ion there. Lovely. If you want to, you can just learn it. Definitely. Personally, I've never learned mechanisms. I just try and work them out. Cool. Good question. What are the two dots? The two dots are the lone pairs, and when drawing arrows, when drawing mechanisms, we must always draw the arrow from a lone pair of electrons to something. So it must always go to an atom or to a bond. Does it go to a bond? No, it should always go to an atom. So it should always come from something, so from a lone pair or from a bond to an atom. So our arrows, especially if they're double-headed, if they've got two sides to the arrow, like 1, 2, that's a rubbish arrow. Let's do it again. If you've got a double-headed arrow, 1, 2, that's a pair of electrons, so it has to come from a pair of electrons, okay? Nice, good question though. And the H plus is an addition. We'd have to add an acid as like a second step to the reaction. Would be to add an acid, and there would that becomes the second step in order to protonate our O minus. Oh yeah, Lucy, you're right. Here I have been a bit lazy and I've drawn it to where the bond is going to form. That's probably a degree level thing. That would be accepted. You could draw, you could say it goes to the hydrogen as well. That would be accepted too. Personally, in my brain, I think it looks neater to show where the electrons are going to, in between the two. But however, if you are a bit lazy with it, you might end up like, so if I did that, for example, I'm not showing it going anywhere, so I'd lose a mark for that. I wouldn't get the mark for that. So you have to be very careful and show your electrons going to exactly where the bond's going. But very good point, good notice. I've totally run out of time. Really sorry, guys, but we are not going to finish this set of slides. And that's because you've been asking amazing questions, and also because we had the technical difficulties at the beginning. So I apologize for that. I'm really sorry, guys. We'll just have to do nucleophilic addition another time. Or if you come to some of our web classes or our drop-ins, I'll show you what those are now, then we can answer those questions then. So super quickly then, just to show you. So we've got some upcoming web classes. Please feel free to go and have a look. Whoops, I did it again. Please feel free to come and have a look at those. It would be awesome to see you guys at those. I won't be them. It'll be different tutors, but they will be there. Yes, this is on YouTube. These are all our YouTube live schedules. And just so that you are aware, we've got loads of courses available. We've got loads of content, available in our courses. So we've got videos, quizzes, revision guides, exam walkthrough videos that talk through exam questions. We've got predicted exam packs these are all in our courses. So this is what our offer will get you 25% off. It gets you 25% off access to all of that. And if I stop sharing this, I can just show you really quickly the website, because I can show you the classes as well. Where's my screen gone? I had it up and it was all handy, and I think it's that one. No, it's not that one. Not that one. No, I didn't click that one. Or maybe I did. I didn't mean to. Oh gosh. Oh, this is not useful. I had it up. Oh, maybe when my laptop froze. Oh no, it's there. I think Oh dear, I think when my laptop froze, it must have closed this. Oh no, it's there. It is there. I did have it. Oh, but it's not happy with me. There we go. Okay, so our courses, I'm going to need to disappear in a second. So our courses, you can go and explore the subjects, go and have a quick look. You can see our timetables. So you can find about for our web classes, you can find out about our web classes. So they take the same shape as this, and they include web classes like this one and exam drop-in sessions, which is exam packets where we have exam questions and we go through whatever content you want, and we discuss any theory that you want, and they are entirely student-led, so they're a really, really useful resource as well. So we've got all of that available to you, and I'm gonna have to disappear, so I can't show any more than that. But really worth going and investigating. Have a quick flick around the site, see what's available. We've got some free resources on there as well that you can have a look at too. The chem classes, there will be more chem classes in November, December. We just haven't put them up yet, but keep an eye on our YouTube schedule and we will let you know those ASAP. So thank you so much. Really sorry, I'm gonna have to disappear, but please use these slides, which are, the link is in the description, or should be in the description. Use the discount code back to school 21 to get you 25% off if you want to investigate what our classes look like on the website. Go and have an investigate, get all of the free resources you can, and hopefully I'll see you in a future YouTube class, or maybe even a future web class. That would be fantastic. Thank you so much for being so brilliant. You've been so chatty and interactive. Hopefully you guys this has been worth it for you. Definitely been enjoyable for me. So hope to see you guys very soon. Thank you very much. I'm going to disappear now. Thank you. Very good. Well done.